Ensuring sufficient and the right kind of nutrient deposition before ovulation is paramount. To avoid those deficiencies like low sphingomyelin we saw, it really calls for sophisticated, phase-specific feeding.
A whole new era of communication in the global aquaculture industry is coming. Now you have the brightest minds in aquaculture right in your pocket. And what's best? You can listen to all of them while driving to a farm, traveling, or running errands. It's never been this good, and it's never been this simple. Welcome to the Aquaculture Podcast Show, the first AI-based podcast in aquaculture, where you'll find cutting-edge insights in everything that's working in aquaculture, nutrition, health, and production.
Okay, let's unpack this. In the demanding world of aquaculture, keeping those production cycles humming is absolutely critical, especially for a staple like Atlantic salmon.
Right, the continuous availability of high-quality broodstock. That's really the bedrock for year-round egg supply.
And meeting that demand often means we're actively adjusting the natural rhythm of things, like spawning seasons. We're not always just letting nature take its course.
Exactly. But the question is, what are the real biological consequences when we start, tweaking nature's timing like that?
It's pretty fascinating to see how deeply a parent's nutrient status can actually imprint long-lasting metabolic traits onto their offspring.
It really is. And this deep dive focuses on research that explores precisely that, the sort of cascading ripple effects of shifting salmon spawning by just a couple of months.
We're going to uncover some fundamental principles here, things related to nutritional programming that have direct implications for how we manage these fish.
Absolutely. Our mission today is to distill the intricate biochemical shifts and the critical insights this work offers.
And connect these biological nuances directly to the robust future of aquaculture, helping you understand the trade-offs, but also the opportunities involved.
Right, when it comes to optimizing commercial salmon production.
Why Genetics turns podcast airtime into brand authority. We don't sell ads, we elevate voices. Curious how far your voice can go to become a reference in the industry and attract more leads? Scan the QR code and discover how we can turn your expertise into unmatched brand authority. Let's transform expertise into influence, starting now.
So the investigation we're diving into looked at Atlantic salmon broodstock, right? Divided into groups.
That's correct. Meticulously divided into 3 distinct groups. You had the early spawners, induced in September.
Okay.
Then a group spawning at the natural time, so November, and a third group where spawning was delayed until January.
And crucially, they were all under controlled freshwater conditions and reflecting industry practice, no feeding after that freshwater transfer.
Yeah, no feeding. And that extended fasting period, that's a really significant factor in everything we observe downstream.
Okay. So physiologically, what happened to the broodstock themselves? Was it obvious?
Well, connecting to the bigger picture, their physiological state was remarkably altered, even if, externally they looked pretty similar. Body weight, length, surprisingly consistent across the groups. But the internal metrics, that's where the story is. The normal season spawners, for instance, they showed significantly higher liver size and a better hepatosomatic index.
Which means better energy reserves, basically, stored in the liver.
Exactly. Superior energy reserves, ready for reproduction. But then you look at the late spawners.
Yeah.
They developed the largest ovaries, which sounds good initially, suggesting plenty of eggs. But they paid a substantial metabolic price for that delay.
How so?
We saw significantly elevated levels of specific amino acids in their muscle tissue. Lysine, valine, isoleucine, leucine. These are the ones the body breaks down for energy when needed.
So they were essentially burning muscle because of the prolonged fast.
Precisely. It indicates intensified muscle protein catabolism. And backing this up, their levels of urea and another compound, alpha-amino and butyric acid, were also highest.
Signaling more protein breakdown, more nitrogen turnover.
Yep. Pushing the fish into a significant catabolic state just to meet energy demands. It raises a big question. How does this maternal stress translate to the next generation?
And the liver analysis confirmed this picture too, didn't it? Especially for the late spawners.
It really did. It got really interesting at the molecular level there. We saw shifts in crucial micronutrients. Elevated folate, particularly the active form, 5-methyl-THF.
Okay.
And increased vitamin B6. But at the same time, methionine levels were reduced.
suggesting changes in those core metabolic pathways, like one-carbon metabolism.
Definitely. An alteration in the flux through that folate methionine pathway.
Mm.
And beyond that, most other free amino acids were significantly depleted in their liver tissue. Again, pointing to severe catabolism.
Wow. And lipids.
Well, interestingly, the early spawners actually maintained higher muscle lipid reserves. But the late spawners, as you'd expect from their catabolic state, showed depleted lipid stores overall. Very different strategies.
So how did all this maternal difference translate into the eggs and the embryos? Was it just a direct reflection?
That's what's fascinating. It wasn't simply a direct mirror image of the mother's condition. There were specific critical differences, suggesting some active programming.
Like what?
For instance, eggs from the early group had higher overall free amino acids, like alanine and glutamine. But, and this is key, they also had significantly reduced folate and sphingomyelin.
Sphingomyelin. That's crucial for neural development, right?
Hugely important, essential for myelin sheaths around nerve cells. So that deficiency is a real concern for early development.
Okay. And the late season eggs. Despite the mother's stress...
Right. Despite the maternal catabolism, they carried the highest vitamin B12 concentrations and elevated active vitamin B6, vital nutrients.
But there was a downside.
Yes, they also accumulated higher urea. That directly reflects the transfer of waste products from the metabolically strained mother. So maybe better B vitamins, but also carrying more metabolic baggage, so to speak.
It's a trade-off then, and you mentioned lipid composition differences too.
Yeah, subtle but significant. We already noted lower sphingomyelin in early eggs, and later at the I stage, embryos from late spawners had reduced phosphatidylethanolamin.
Another key membrane component, especially for the nervous system.
Exactly. So these aren't just bulk nutrient shifts. They're hitting very specific foundational building blocks for development.
And what about later, at the I stage? Did those differences persist?
They did. Early embryos still had higher branched chain amino acids. Normal embryos had more alanine, aspartate, tryptophan, different priorities, it seems. Late embryos kept showing that maternal legacy of higher B12 and B6. And interestingly, cystathionine popped up uniquely at this stage, highest in early embryos. Suggests a role, maybe delayed, in regulating one-carbon metabolism later on.
Okay, so we've got all this complex biochemistry, this maternal programming. What did it actually mean for the offspring, for larval growth?
Yes. The larval weight at first feeding, that's a key indicator of initial vigor, future potential. And it was strongly influenced by the spawning season. The results here might genuinely surprise you.
Go on.
Okay, so early spawning produced significantly lighter larvae, only about 142 milligrams on average.
Lighter, okay. And normal.
Normal spawning resulted in much heavier larvae, a robust 184 milligrams.
Right.
But here's the kicker. The delayed spawning group, remember, their mothers were under significant metabolic stress.
Yeah.
They produced the heaviest larvae, averaging 192 milligrams.
Wow, heavier than the normal group, even with the stressed mothers.
Exactly. It's counterintuitive, isn't it?
It really is. So why would that happen?
Well, the study suggests that even under that severe maternal catabolism in the late group, there was an adequate, maybe even prioritized, allocation of essential nutrients to the oogocytes.
Like nature ensuring the next generation gets what it needs, even at the mother's expense.
It certainly looks that way for initial growth, enough to ensure robust initial development. But that wasn't the case for the early spawners. Their progeny were significantly lighter.
Indicating maybe insufficient nutrient deposition, incomplete maturation.
That's the likely explanation. Insufficient nutrients during an advanced, perhaps rushed, maturation period. It's a striking example of resource allocation prioritizing offspring start weight.
This whole picture really underscores how central those metabolic pathways are, doesn't it? Like the Cahill cycle, one-carbon metabolism.
Absolutely. They're orchestrating this incredibly complex intergenerational nutrient transfer, affecting amino acid pools, redox balance, methylation capacity.
All critical for future growth and the ultimate phenotype of the fish.
Precisely.
So, connecting this back to commercial production, what are the big takeaways for the industry?
Well, the results highlight an absolute necessity for really fine-tuned broodstock nutrition. You can't just expand the spawning window for year-round supply without adapting the diet very carefully.
Right, it carries risks otherwise.
Significant risks to offspring performance.
Oh, yeah.
Specifically, those broodstock undergoing prolonged fasting, like the late spawners, they could really benefit from diets designed to mitigate that muscle breakdown, preserve amino acids.
Feeding for resilience, essentially, and for early spawning.
Ensuring sufficient and the right kind of nutrient deposition before ovulation is paramount. To avoid those deficiencies like low sphingomyelin we saw, it really calls for sophisticated, phase-specific feeding.
And this also highlights how sensitive this whole reproductive programming process is to stressors, right? Especially looking ahead.
Definitely. With changing global conditions, increasing demands, aquaculture systems need to anticipate these potential disruptions. Adjusted feeding, precise environmental control, they become even more essential to safeguard that intergenerational growth potential.
Precision aquaculture, basically.
At its finest, yes.
So, summing up, the timing really matters. Early spawning compromises initial growth, late spawning stresses the moms but can still yield heavy larvae if nutrients get prioritized.
But the normal spawning window seems to provide that optimal balance, physiologically speaking, for both parent and offspring. That's the key takeaway.
So what does this all mean for you, our listener? It really reinforces that nutritional and metabolic programming are absolutely central to sustainable aquaculture productivity.
The real challenge, and maybe the bigger opportunity, lies in how precisely we can keep fine-tuning broodstock nutrition and management.
Not just to secure production, but to actively enhance the growth, health, resilience of future salmon generations.
Exactly. It makes you wonder, doesn't it? What other subtle yet profound intergenerational influences might be out there waiting for us to uncover and optimize?
Not just in aquaculture, but across the entire agricultural landscape. Something to think about.
If you enjoyed this episode, make sure to follow the Aquaculture Podcast Show on your favorite platform. And don't forget to follow us on LinkedIn, Instagram, and Facebook to stay updated on the latest episodes and industry insights. Thanks for tuning in, and we'll catch you next time.